We're going to start right in. The quiz will be later in the lecture. We're coming out in the home stretch. There's 4 lectures left. I tried to ask you people earlier if they have special requests. But as the lecture goes on, if you come across something you go, oh, such and such seems confusing to me, could you spend some time on that? I could take a break right then, or I could prepare it. So why don't you catch it when you can, something that seems generally confusing to you. And then I'll check and see whether other people want me to spend time on a given thing. Okay. Where are we in this class? The class is about how things move. Those things are particles and rigid objects. The main equations we have in mechanics are force equals mass times acceleration, and torque equals rate of change of angular momentum. In order to plug in those equations, we have to evaluate the right-hand side, which has acceleration, or rate of change of angular velocity. Lydia, please be quiet. When you have things moving around in complicated ways, like they're rolling, or they're gears, or they're sliding, sometimes it's hard to keep track of the motion. And that's the sort of tricky part of the course we're in now, is keeping track of motion of things moving funny ways. At the beginning of the semester, we have acceleration we can think of just in Cartesian coordinates. That's still correct. It's just not the easy way to do problems where you have moving parts. So we have these various other ways of keeping track of things. Polar coordinates, another way you can figure out acceleration. Then we had this relative frames moving around. Another way to keep track of velocity and acceleration by seeing how parts are moved, how dots are moving on objects which themselves are moving. And that's all these complicated formulas with omega cross r and omega cross v and so on. And today we're going to do the last, I believe, of the complicated ways of keeping track of how things move. I think I made a mistake in that we have homework on what I'm showing you today due tonight. If you feel like you don't have time to do it, or somehow it's not fair, then just say so and then hand it in late. Okay, so this is this topic called path coordinates. So here's how path coordinates work. If you have something moving around, and say we're going to keep track basically of how it moves around by how it moves around relative to some fixed reference frame. So we have some fixed reference frame. As a thing moves around, let's say this thing is a dot, and we're going to keep track of this dot moving around. We have a dot moving around on the plane. As it moves around, it progresses from some initial point onwards and has some arc length s. This is a distance that moves along some curve. And if we catch it, we can now make up some new vectors that we're going to use to keep track of the position. For polar coordinates, the vectors that we used were based on the position of the particle relative to the origin. In this case, we're going to make up base vectors which are based on the velocity of the particle. So what we have is a tangent line like this, and we invent new vectors. One vector that we can keep track of is this velocity. That is the velocity. And another vector we can make up is a vector which is parallel to the velocity, but it's a unit vector. So we take the velocity, divide by its magnitude, and we call that the tangent vector. Well, if we have a tangent vector, we can make up a vector which is perpendicular to it, and we call this the normal vector. So the new vectors we have are the tangent vector, which we can define as v divided by the magnitude of v. Another way of looking at it, though, is we can look at an increment in the position, any increment in the position, and divide by the magnitude. So that would be what we call dr ds. So this doesn't have the velocity in it at all, it just has the path. It's the rate of change of the position vector with arc length. And this is already a unit vector, because the change in position vector is itself in magnitude the same as the change in arc length. Then we have, so this is called the unit tangent. Then we have the unit normal vector. And if we're in 2D, we could find that thing by just taking k cross et. But this idea of path coordinates is actually a three-dimensional concept, so we don't want to do that. So what we do is we say we look at the derivative of et with respect to s, and we divide by the magnitude of that. Or we could do the opposite, I mean not the opposite, but the same thing we did up there. We could look at the rate of change of et with respect to t and divide by the magnitude of that. And this thing is called the unit normal vector. Associated with these vectors is the idea that at any instant in time, you can think of a curve as being a dot. That tells you where it is. You can look at what's like the first term in the Taylor series, which is the tangent, which tells you the tangent line, which is a velocity. And then you could look at the second term, something like the second term in the Taylor series, which tells you how curved this curve is. And this is the idea of this curve called the osculating circle. And this osculating circle has a radius, which we call r, and this is r rho, which is the radius of the osculating circle. Which is also called the radius of curvature. Now the word osculating, if you look it up on the internet, actually I've never looked it up on the internet. We could just play that game right here. I've said this is true, but I've never actually done this. So let's just see if I'm lying or not. Spelled with an S. Now I have the beach ball. Osculating. Definition. Osculate. To kiss is the definition. So, that's not a joke, that's what what?
Osculating.
Osculating. I would like to osculate you, I guess. I feel like osculating, I don't know. But the idea is that this circle here has this very intimate relationship with this curve. It's not just that it touches the curve. It's not just that it's tangent to the curve. It's that it shares the same curvature as this curve. So you can think of any curve at any instant as having this very intimate relationship with some circle. They're really snugly together. They're kissing. They're osculating. If you find out what that is, that circle that just fits this so well, and find the radius, that gives you this osculating, this radius of curvature. So what do we do with this for the kinematics? Now that we have that description of the curve, as something moves along, we can say the velocity at any instant in time, no matter how something is moving, is a speed times the unit vector in its direction. That's always true. How could it not be true? Velocity, any vector is itself and it's itself divided by its magnitude times its magnitude. Itself divided by its magnitude is a unit vector in the direction of the velocity, and then times the magnitude again. So this is the direction part of the velocity, and this is the magnitude part of the velocity. Now if we want to figure out what the acceleration is, that's the rate of change of velocity. Now of course on the side here, we could have put that the velocity is x dot I plus y dot j, and then we can say what's the acceleration? It's x double dot I plus y double dot j. But now we want to think about this a different way. We want to think about it this way. So what's the acceleration? It's v dot times the unit vector in the direction of the velocity plus v times et dot. But what is et dot? Well, here's et dot. So if we take et dot and rearrange it, we have this En. So here we have the rate of change of Et with respect to Es. We have dE dt ds. So we can rewrite this then as V dot Et. And then we can put here a V times Et dot. But Et dot is certainly going to be proportional to V, and it's going to be in the En direction, and it's going to be divided by this radius of curvature. Now, why is that? That's an extra little bit of geometry that says that this unit vector changes per unit arc length depending on the radius. So I think I'm going to skip that geometry just to save time. But this is the key formula here. What does that say? It says that any particle, no matter how it's moving, has the same acceleration as if it was moving in a circle. Here's the part that we used to think of as being like v squared, like theta dot r times e theta. That's the rate of change of speed along the circle. And this is the part that we think of as being v squared over the radius of the circle. So that the formulas we had for polar coordinates for particles moving in circle actually apply to any particle, no matter how it's moving, in any complicated way, even in 3 dimensions. That is, at one instant in time, there's always a circle. It might be crooked in 3 dimensions, and you can calculate the velocity and acceleration by looking at how fast it's traversing the circle and what the centripetal acceleration is towards the center of the circle. Now let me do an example that uses these ideas a little bit. Okay, questions about this? For this part, I didn't do the algebra. I didn't draw the picture. But if you want to draw the picture to try to derive that formula, you'll put in a little delta theta here, and you look at how much Et changes per unit theta as it goes around. Okay, any questions? Yes?
To use this, do you know the entire path of the particle, or like the path up to a certain point?
No. The question is, what does it mean to use a formula? One way of using it is to use it to build your intuition. So we have this intuitive fact that we can think of any particle as it moves in any complicated way as having an acceleration that has 2 parts to it. One part is that it's changing its speed, and that gives you an acceleration tangent to a path, and one part which says it's changing its direction, and that's this v squared divided by the radius of curvature. So that's just a fact that we can use for intuition, independent of whether we know the particle's path in Cartesian coordinates or polar coordinates or anything else. Or there might be a problem where we don't know the position of the particle as a function of time, but we know the path of the particle. And then we can use this to help us figure out the acceleration. So that's the example I wanted to do here. So let's say I had a coordinate system, an x and y coordinate system, and I have a particle which is sliding in this bowl, and this bowl is the equation y equals cx squared. And this particle is going to slide in this bowl, and it's going to be a small little particle here with the mass m, and we're going to have no friction. And we're going to have gravity here like this, and if we want them, we have I and j like this. And the question is, can we figure out how that thing moves on that path? Okay, so how are we going to figure that out? Well, we can draw a free body diagram of that thing. And there's this path here like so. And in that free body diagram, we have mg like this. And we have a normal force. And that normal force is n times some unit vector in the en direction. Now that is our normal to the path. So we do not know, in this case, how this particle is moving as a function of time, but we still know the direction of the normal to the path. Do you want to do that out loud? Please.
Okay. So I understand how like the acceleration vector correlates to the theta squared over r, but how do you go from the a tangential dot to the square?
How do I get from here to here?
Yeah.
I explicitly did not show that to you. I can show it to you, but I didn't prepare it, so it would take me a minute. The reasoning involves putting in a little angle here and looking at how this unit vector changes per unit arc length, and getting a formula for det d theta, which will be in the en direction. Okay, so the missing piece here is d d theta will be equal to en, where theta is this distance here, and then we have to have the ds is equal to rho d theta. And if we put these two together and then use the chain rule on theta as a function of time, then I believe in a step or two you will get to here. Okay? Which I could do, but you risk watching me getting confused. If you want to watch me do it and possibly get confused, I will volunteer to do that. All in favor of having me do that step in the derivation? All opposed? There you go. It's in the book. I think I can do it. It's just that I didn't line up the algebra in my head already. Okay. Now what is this? This is the unit vector tangent to this thing. Now, if we're going to figure out how this thing moves, we have our equation, which is that F is equal to ma. What is that in this case? It's minus mgj plus n e sub n is equal to the mass times the acceleration. But this thing has how many degrees of freedom? So it has 1 degree of freedom. If we know the x-coordinate, we know where it is. Or if we know the arc length, we know where it is. Or even the y-coordinate. So it doesn't seem right to have this whole equation here and have two different coordinates for the acceleration when this thing is moving along some known path. So what we can try to do is eliminate this thing that we don't know and don't care about. So we can take this equation here, and we can take the dot product of it with et. Actually, we could take the dot product of it with the velocity. We can take the dot product of it with any vector along the motion. And then we will get from this the equation minus mgj dotted with the tangent vector plus 0 equals ma dotted with this tangent vector. now, if we want to figure out what any of these things are, we have that y is equal to cx squared. So y dot is equal to 2cx x dot. So the velocity is equal to x dot I plus 2cx x dot j. And this way we have the velocity all expressed in terms of x. So now we can write that the unit tangent, if we need the unit tangent, is x dot multiplied by the quantity I plus 2cxj divided by the magnitude of this thing. What's the magnitude of this thing? Is the magnitude of x dot, which is going to be x dot, multiplied by the magnitude of this thing, which is the square root of 1 plus 4cx squared. Or we could just use the velocity here like this. So if we want to save some algebra, we could also write or at minus mgj dotted with the velocity plus 0 is equal to ma dotted with the velocity. Okay, so now we have minus mgj dotted with the velocity, but the velocity is x dot plus 2cx x dot j is equal to m, and now we can put x double dot I plus y double dot j dotted with the velocity, and we have x dot I plus 2cx x dot j. Now what do we get from this whole mess is this will give us a differential equation that only has x in it. So this is a 1 degree of freedom system. So by this means we have reduced this to a single differential equation involving only x. So if we want to see what that gives us, this term has in it only the second term. So this gives us minus mg 2c x dot equal, and then on the right hand side we have to put all this stuff together. We have an m, we have an x double dot times x dot, m x double dot times x dot, and then we also have a y double dot times and y double dot is yet to be worked out. So we have also plus y double dot times 2cx x dot. And if we assume x dot is not 0, we can cross that off. Yet to be filled in is this y double dot. What is y double dot? We have to take this thing and take its derivative. So it's 2c times the quantity, and then we have x dot squared plus x double dot. So that then turns into a 2c x dot squared x times x double dot. And then what we get from this whole thing is that x double dot equals some mess here, and I'm going to skip that algebra. But this is what we would call the equation of motion. Okay. So I didn't use the path coordinates explicitly, but I used the idea of keeping track of the path and then taking a dot product along the path. Okay. Yes?
I believe it's supposed to be c squared and a little bit.
Did I miss a c squared here? There. Student, or semi-student, or student plus. Have I fixed it correctly? Okay. This example, it's a mess, but it's not that bad of a mess. This particular example I learned from a guy in applied physics who told me what was wrong with Newton's laws is you couldn't do a problem like this to get this differential equation without Lagrange equations. And so I took that and said, I don't think that's true. And then we compared notes. Just doing this algebra I just did compared to the algebra of Lagrange equations. You don't even know what Lagrange equations are, but there's some. Who's heard of Lagrange equations? Just heard of it. Okay, you've heard of them. People advertise them as so great. It turns out there's no less algebra or less work in doing this with Lagrange's equations. It's almost all the same calculations, and you can do fine without Lagrange equations. Okay, I want to go on now and talk about mechanisms and so on. And I'm going to start with a puzzle problem. Some of you will know this puzzle problem already. I would like those of you who know this problem already to keep your mouths shut. So I will, if I ask you a question like, do you know this problem, you could raise your hand, but please don't yell out answers if you know the problem already. Okay, so I'll be back in a minute. Bicycles. Okay, so here we have a bicycle. It's not a special bicycle, except for I bought it for my wife for a present, but besides that, it's not a special bicycle. Like it's not rigged up any special way. And I'd like to take this bicycle and make it so I don't have to worry about the steering. So this is not unlike that radio show I played for you the other day. This one's not about steering. If I can get this to work. There's that one.
Pull the brakes.
That's going to mess up the experiment totally, isn't it? One suspects.
Try hooking it to the other side of the brake line.
There's a good one. I'll get it. Okay, there's a good one. Okay, so now I've got the steering sort of locked up, or semi-locked up. So, okay, now I'm going to put this on the bench here, and I need someone to help me balance things. A volunteer? You're too far away. A volunteer up here. Okay, so your job is to stand back where I'm standing and just don't let the bike fall over. And you want to carefully make it so nobody suspects you of pushing the bike forward or backwards. So you just want to balance like that. Okay, now so here's the puzzle problem. If somebody comes along and pulls on this pedal, pulls in that direction, does that cause the bicycle to go that way or that way? So here's the pedals. If you want to see what the pedals do, that's what pedals do on bicycles. So if I pull on this pedal in that direction, which way does it make the bike move? Now, if you've seen the puzzle before, who's seen this puzzle before? Raise your hands. Is this another one you did in Physics 112? Who did not take statics from me? Okay, there we go. We have 8 people who can do the puzzle. But that was statics. That was the direction of the force, not the direction of the motion. Okay, so you know how this goes. Curses.
You should ask if they remember it.
Who remembers the answer?
It's on video now.
It's on video now. Okay, so I pull it this direction, it goes that way, right? Now, when we did this in statics, the puzzle was what force do you have to apply to keep it from moving? Here the question is what's the direction of the acceleration? Slightly different puzzle. Very slightly. This thing goes back like this. Does anybody remember a reasonable explanation for why it goes back like that? Yes?
Right now you're applying an external force, so the sum of the forces.
I'm applying so when we draw a free body diagram of this bicycle, there'll be a force in that direction. But when we draw the free body diagram, there will also be a force in that direction there. So the issue is, which is bigger of those two forces?
Well, I was thinking before you gave away the answer that it would go forward because bikes give a mechanical advantage.
Right. So you're supposed to think it goes forwards. That's why this is a good puzzle, right? It's like the wheel. It's like the movie problem. Yeah. Yes.
But I mean, just like forward, like any sort of problem like this, you're applying a force backwards. Why would it go forward? You just apply it.
Okay. So let me just tell you the fact of the situation here.
It goes in the way you apply it to.
If your reasoning was correct, I'm applying a force backwards, why would it go forwards? You could say with confidence it goes backwards. So let me tell you something. There is a different bicycle, which I do not have here, in which when I push on this backwards, it does go backwards. So this answer that this it does go forwards. The answer that this goes backwards when I push backwards is actually a quantitative result about the gear ratio of this bicycle. It turns out it's about all bicycles you can buy, but not all bicycles you could build. So if this had a very small sprocket here and a big sprocket here, how small, how big, I'll tell you a way to think about it. This would go forwards when I push backward on the pedal. Because of the mechanical advantage. So let's try it a different way. Are you strong enough to hold the bicycle up in the air? So if you just think of this as a machine where there's a bunch of gears and there's a force here and a force here, the question is this force at my left hand bigger or smaller than one at my right hand? That has to do with the gear ratio. Now, what do we know about transmissions if they're lossless and frictionless is that the work into them equals the work out, or the power in equals the power out. So if I want to know the ratio of this force to this force in magnitude, it's equal to the ratio of the velocities. Whichever one is moving slower is the one with the bigger force. So the whole question about which way the bike moves has to do with whether this force is bigger or this force is bigger when we look at this transmission, which is also a question about which moves faster on this bicycle, the pedal or the wheel. Now people say, oh, the reason you have this transmission is for mechanical advantage. Remember, in the world of pulleys and so on, the word mechanical advantage has two opposite meanings, which is easy to confuse. One is that you multiply motion, and the other is that you multiply force. The reason you ride a bicycle is because you want to go fast, not because you want to climb mountains. And so the mechanical advantage you get with the bicycle is that motion is amplified. For a given speed that you move your foot, you move faster. So that tends to make you think that this velocity should be higher than this velocity. Because how fast is the bicycle moving forwards is how fast this tire is moving backwards when I hold the bike still. And when you're pedaling a bike at a given speed, for a given foot velocity, you're going faster than you do when you're walking. That's what bicycles are for. Okay, so knowing that is another way to say it. When you watch people bicycling by, even though you're looking at them and you're seeing their bottom foot go backwards relative to the bicycle, if you just hold your gaze very carefully, what you'll see is that when a bicycle is going forwards, the pedal is going forwards. If the pedal's going forwards, that means this velocity is higher than this one. If they're equal, then you see the pedal still as the bike went by, and you don't. You see the pedal going forwards. And that's true for all bicycles you can buy, though not all conceivable bicycles. What does it depend on in the ratio of this length to this length to this length to this length, like you did in the homework in TAM 2020? Okay, so now, if you want to try to analyze this as a machine, the simplest way to analyze this is with energy analysis. So the energy analysis goes like this. And we're going to apply a force here like this. And I'll apply a force here at this point P for pedal or for point. And here we're going to have this backwards force like this. If we pick a coordinate system like this, where we have I in this direction and J in this direction, when we draw a free body diagram of this thing, there'll be all kinds of forces. A force here, a force here, a force here, an mg force here. Which of those forces do work when this bicycle is moving in this problem where I apply this external force?
Are you sitting on the bicycle?
I'm not sitting on the bicycle, I'm standing in front of you. In this problem, I'm not sitting on the bicycle, I'm standing in front of you talking about the bicycle, applying a force to the pedal from the outside. Which of those forces do work on the bicycle? Yes? Not you? Yes. Both of them. There's 5 of them here.
Both of the forces in the I direction.
Okay, and that is not correct. So the work of a force is the force times the velocity, or the power of a force is the force times the velocity of the point with which it makes contact. And that wheel point on the ground is rolling, so its velocity is 0. So this is the only force which does work. So we have, on the left-hand side, the power in is minus Fi, dotted with the velocity of the pedal, which I'll call velocity of the pedal I. That's how fast the pedal is moving forwards. And that has to equal Ek dot. Now if we start this from rest, Ek dot has to be bigger than 0. What does that mean for these things here? That means that if F is positive, that Vp has to be less than 0. Now this reasoning did not have to do with the gear ratios. Independent of the gear ratios, if you have a passive machine, which is initially at rest, and you push on it at one point, and all of the other forces do no work except for the one you're applying to, that point has to yield. When you push on things, they go in the direction you're pushing on them. If I pushed on this, and this pedal itself came forward, it would be doing work on me. Where's that going to come from? The atom bomb that's inside here, there's not one in there. There's not an energy source in there. If I push on something and it's a passive system, and it's starting from rest, I have to do work on it, which means the pedal has to go backwards. So I push on this, the pedal has to go backwards. On this bicycle, the pedal goes in the same direction the bicycle goes. Looks like it's going backwards relative to the bike, but in the room, the pedal goes in the same direction as the bike goes. On some other bike with very low gear ratios, they go in opposite directions. And on all bikes, when I push on the pedal, the pedal goes in the direction that my hand pushes on it. So your initial intuition from before you saw the 202 exam, or if you didn't take 202, that the pedal goes that way is correct. The mistake in your intuition is to not realize that when a bike moves, the pedal and the bike move in the same direction for real bikes. Okay? Now this is actually all I wanted to talk about today, so for a change I'm like way early. So we have some choices. You can watch me try to derive that polar coordinate, path coordinate thing. You could ask me a different question, or we could end early. All in favor of path coordinate derivation? All in favor of something else that you ask about? Random things. All in favor of ending class early so I can pay back my debts from all the times I've been late? Okay, how about one quick question and then we'll go early? Okay, so, yes?
If you apply force to the pedal that's like horizontal and you lift it up, does gravity work? So
You want the...
so in that case you'd be pushing down. And if you had it going
I push it down, this bike's going to go forwards. There'll be some intermediate angle when I push on it. It will go neither forwards or backwards. It has to be that the dot product of the velocity of the pedal with my finger is such that my finger does work on the pedal. Right? That address your question? Okay. Okay.